In this session, I will show you how to use MIPSfpga performance counters. First, I will give you an overview of performance counters. Next, I'll talk about the MIPSfpga performance counter registers. And then I'll show some software macros that you can use, as well as some examples. Performance counters are useful for testing functionality and measuring performance bottlenecks. So we can measure events such as cycles, instructions completed, data cache accesses and misses, and so forth. Performance counters are implemented inside the system control coprocessor 0 of MicroOptiv. MIPSfpga has two performance counters available, performance counter 0 and performance counter 1. Each performance counter has two associated registers, the control register and the counter register. The control register controls what we're measuring. So for example, if event is set to 0, we're measuring the number of cycles. If it's set to 1, we're measuring the number of instructions completed, and so forth. The counter register gives us the number of that event, so the number of cycles, the number of instructions, etc. Each of these four registers is indicated as CP0, coprocessor 0, register 25, and then depending on the select number, that indicates whether it's program counter 0 or 1 and a control or a counter register. For example, PC0, its control register is indicated as CP0 register 25, select equals 0. PC0's counter register has select equal to 1, and so forth. We use a macro to configure the program counters. So the macro shown here moves value to a coprocessor 0 register identified by reg, select. So for example, configure performance counter 1 to measure the number of instructions completed. We'll set CP0 register to register 25, select equal to 2, event filled is 1 and K filled is 1, as shown below. We use a second macro to read an event on the performance counter. So for example, if we want to read performance counter 1 into a variable, we'll say variable equals this macro register 25, 3. We introduced two new macros to initialize the performance counters and read them. So init performance counters initializes PC0 to measure the number of cycles and PC1 measure the number of instructions. The read performance counts macro reads the number of cycles into the num cycles variable and the number of instructions into the complete instructions variable. We also provide skeleton code for using the performance counters. It begins by initializing the performance counters. You would then insert your own code that you want to measure, and then it reads the values of the performance counters and displays them on the 7-segment displays. If the switches are 0, it displays the number of cycles on the 7-segment displays. If the switches are equal to 1, it displays the number of instructions executed. So now let's look at an example of using the performance counters to calculate CPI, or the number of clock cycles per instruction. Here's some example code that performs a loop 1,000 times and then continues. Let's first analyze the CPI using the ideal pipeline processor from Digital Design and Computer Architecture by Harris and Harris. Jumps and taken branches require 2 clock cycles, and branches that are dependent on the result of the immediately prior instruction also require 2 clock cycles. All other instructions require a single clock cycle. The first 3 instructions require 3 clock cycles, and then each iteration of the loop requires 7 clock cycles because of the dependency of the branch of equal on set of less than causes branch to have 2 clock cycles instead of 1, and the jump at the end of the loop requires 2 clock cycles as well. At the very end of the loop, the last 2 instructions, the set of less than and the branch of equal, require 4 clock cycles because of the dependency between the branch and the set of less than, and then the branch requiring an extra instruction so that it can take the branch. So the total number of cycles required is 7,007, and the number of instructions executed is 5,005, giving us a CPI, or number of clock cycles per instruction, of 1.4. Let's compare this with the pipeline from the MicroOptiv processor. Each jump or branch requires 2 clock cycles, and in this pipeline, a branch that's dependent on the result of a prior instruction only takes 1 clock cycle. All others also take 1 clock cycle. although we have to also take into account the non-ideal memory, the instruction cache miss delay. So for this processor, we have 3 cycles for the preamble as before, 7 cycles per iteration because each of the branches and jumps take 2 clock cycles instead of 1. And finally at the end, the last 2 instructions, a set of less than and branch of equal, require 3 clock cycles because the branch takes 2 clock cycles. For this one, we have a CPI of about the same, 1.4. Now let's use performance counters to measure how the MIPSfpga processor performs on this code. We're going to add the following assembly instructions to our skeleton code and then test it on our Nexus 4 DDR board. Note that the MIPS compiler inserts a no-op instruction after each branch or jump to fill the delay slot. We'll start by loading the MIPSfpga system onto our Nexus 4 DDR board. We can use the bit file located in the Lab 13 folder, shown here. We'll restart the system, and we see the default program running. Now we'll load our program. I've modified the skeleton program to include that assembly code. Now if we move the position of the switch 0 to 1, we can see that it shows the number of instructions completed, 7012. If we move it to position 0, we can see the number of clock cycles, 7025. So the number of clock cycles we measured with the performance counters was 7,025, and the number of instructions completed was 7,012. Recall, however, that instruction count included those no-ops that were inserted after each branch and jump. So we'll subtract those from our instruction count to get 5,011. The CPI that we measured then using the performance counters was about 1.4, pretty close to the number that we got analytically. We can also consider the instruction cache misses, but it's such a small program that after the first iteration, there are no instruction cache misses. So it allows our empirical result to coincide almost exactly with our analytical result. Note also that a few extra instructions were added to accommodate the performance counters. So let's go ahead and try to optimize our code so that we can fill those delay slots, those branch delay slots, with a useful instruction instead of a no-op. So the first thing we do is set no reorder so that the compiler won't reorder our code. And we put the loop variable increment right after the jump. So jump loop, and we put that increment of I right after that loop variable. And then we add the value after the branch. So the body of the loop we put right after the branch instruction. We have to undo that last addition, so we add a subtract instruction after the done label as well. So let's go ahead and take a look at how this code performs on the MIPSfpga system. So let's go ahead and load this optimized code onto our system. Now we can see that the number of clock cycles is 5,026, and the number of instructions is 5,014. So now we can calculate the CPI from the measured number of cycles and number of instructions, and we see that it's approximately 1. This is the ideal CPI that we would get. There are some effects, such as the instruction cache misses and a few extra instructions due to the performance counters, that make it not exactly 1, but it's pretty close. So in this session, I've showed you how to use performance counters on the MIPSfpga system and how to even optimize some code and show that effect using the performance counters.